Great. Well, thank you. Thank you to the organizers. This has been a fantastic. I was just telling Jason how much I've enjoyed this conference, and it's also gratifying to see how many papers there have been that have been within family papers. So I was going to say that's the future, but I guess the future is now. So this talk was supposed to be joint with David. Unfortunately, David wasn't feeling well and had to cancel at the last minute. So you'll get me for an hour. I'll try to keep it shorter. I want to have time for discussion. So actually, in terms of questions, I'm happy to do have discussion at the end, but I'm also happy to have questions throughout. And I think it'll be more fun, to think through some of these issues together. What I thought would be maybe most valuable to do in this session is to think through some of the issues that will come up, are coming up, and will continue to come up as the field continues to move in the direction of doing analyses with PGIs in general, polygenic indexes in general, and within family analyses with PGIs in particular. So I should acknowledge that much of what I'm going to say is things I've learned from others, from many colleagues over the years, including many of you. And I'm particularly grateful to Patrick, who's here, and Alex Young, who's not here. And I've also listed a few funders. I would contend that in most applications, including pretty much all of the papers that we've heard in this conference, even if we're using a PGI which is not maybe confounded with environmental factors, the thing we're actually interested in is the causal effects of genotypes. There are some exceptions. You could imagine applications where what you want to do is control for as much variation as possible to get more precise treatment effect estimates, and there you may not, you wouldn't care if the PGI is just causal, or you might just want some index of heterogeneity. But most applications, I think what we're interested in is causal effects. So genetic data is special in a number of ways. It's fixed at conception, which means it's prior to the choices that, any choices that a person makes over their lifetime. But another way in which it's special is that it is random, conditional on the parental genotype. So that gives us a wonderful natural experiment that we can exploit to get at these causal questions that we may be interested in. And we know why it's random. It's this biological process of meiosis. Now, just as this is a bit of an aside, but to an economist outside this literature, this may superficially resemble the use of within-family variation in environments. At one time in economics, there was a period where there was some enthusiasm about using MZ twins and the variation in MZ twins to try to get at causal effects. So, for example, looking at differences between MZ twins in their schooling, and then looking at how that related to differences in earnings, and using that to try to see something about the causal effect of schooling on earnings. The problem there is that there's some reason why so the idea was that you were then holding constant genetic factors. Problem is there's some reason why they're different in their schooling that may also explain why they're different in their earnings. So that's not exogenous environmental variation. This is different. With genetic data, there really is a random assignment conditional on the parents. Okay, so first thing I want to do is, before we even get into within family analysis, I want to think, just from first principles about what we mean when we talk about the additive model. What is it we're assuming, and what are we not assuming, and what do we mean by PGIs? I think it's useful to revisit some of these fundamental questions once in a while, because I think there's actually a lot of misunderstandings. It's also going to be the basis for a lot of what I'm going to talk about later. And I think it's worth noting, even a lot of geneticists aren't entirely clear on some of these issues. They just don't think they don't think that much about the foundational questions. And I think we as economists are actually well equipped to work through some of these conceptual issues. Okay, so where does the additive model come from? It's actually very simple. We have some data. We have, imagine an infinite data set where we have, so it's a population where we have data on individuals' phenotypes. We have for each individual their genotype at a bunch of locations that I'm indexing by K. And we can collect that together into a genotype vector for each individual. And I'm just going to work with demeaned phenotypes to keep the notation simpler. So I'm going to denote that by y tilde. So the additive model just comes from the data. We just take the data and run a population regression of the demeaned phenotype on the genotype vector and some vector of controls that we may have in our data. Because it's a regression, we get that the residual is orthogonal to the genotype vector and to the controls. And that's it. So that's the additive model. We've actually made no assumptions here. We've just taken our data and decomposed it in some way, so we get orthogonality. So, that's here's, I think, a first misconception that is pretty common. People often think that when they write down an additive model, there's some assumption built in that we're assuming away dominance effects, nonlinear effects of genotype or gene-gene interactions and gene-environment interactions. In fact, there's no such assumption. The additive model is just a way of describing the data. So these things, where are they in the model? I mean, of course, in reality, there may be such effects. And the way to think about it, for example, with dominance, is that this linear term, x beta, is the best linear fit, the best linear predictor that captures those nonlinear effects. And the part that you're not explaining, which is orthogonal to the best linear predictor, is getting put into the error term. And that's true for the others as well. Okay, so there's a concept that goes by different names. People think of it as like the true, sometimes you hear the true polygenic index. I like the terminology additive snip factor. And what it is, when I use that term, what I mean is the genetic piece of this equation. But we usually standardize it so that it has variance 1. So I'm going to write this additive snip factor as this genetic component of the phenotype in the additive model, which is divided by the standard deviation of the population. And one thing I want to highlight, because this is, again, something that is important, but I think not always fully appreciated, is that what this additive snip factor is implicitly a function of the control variables that were included in the regression. So this is going to come up later because when we talk about within family variation, these controls will be things like family fixed effects or parental additive snip factors. And then this GI is going to be a causal effect of SNPs. And if we don't have exogenous variation, then this is not in general going to be a causal effect. But it also matters in other ways, whether we control for sex or don't control for sex, or control for principal components or don't control for principal components. In the GWAS, that's going to affect this additive SNP factor that we're talking about. So that's going to matter for the interpretation of the additive SNP factor, and then downstream for the PGI, which I'll get to in a moment. Okay, so these betas, the way to think about the betas in this additive model is that they're average genetic effects. They're averaged across the individuals that we have in the population. They're averaged across the genotypes in the population because there could be gene-gene interactions that we're averaging over. It's averaging across environments. So one thing, that's another misconception that you hear a lot is that somehow, when you do GWAS and you find SNP associations, you're finding the associations that are somehow the ones that are particularly robust to things like gene-environment interaction. They're the ones that have these robust main effects. It is true that if you have a SNP that has no effect on average across different environments, but happens to have a positive effect in some environments and a negative effect in other environments, you won't detect that SNP in a GWAS because the average is out to 0. But it's not true that the SNPs that you're identifying in a GWAS are somehow unlikely by virtue of having been identified in a GWAS, unlikely to have G by E effects. It's just that they're, what you're getting in the GWAS, or what this beta is an average over the distribution of environments and whatever G by E effects there might be. Okay, so I think that's useful to understand. The beta, like the additive SNP factor, the beta has a causal interpretation as causal effects only if the genotype vector is as good as random conditional on the control variables. Okay, so now what is a polygenic index and how does it relate to the general setup? Well, a polygenic, we don't know the betas, so we can't construct the additive SNP factor. The polygenic index is what we can construct based on estimates that we get for the betas from a GWAS. I'm going to call that G hat. Of course, the GWAS is doing SNP by SNP estimates, but then the methods that we usually use to construct the PGI tries to adjust for the linkage disequilibrium between the SNPs. So it's effectively, you can think of the PGI weights as effectively giving us estimates of the betas from the multivariate regression. That's our underlying theoretical model. So the way to interpret the PGI is that it is a standardized noisy measure of the additive SNP factor. So this is worked out carefully in the PGI repository paper, Becker et al. So the PGI is the additive SNP factor plus a term which is mean zero estimation error. It comes from the estimation error in the GWAS, which is uncorrelated with the true additive SNP factor. And then because both G and G hat are standardized to have variance 1, we have to have a scaling factor to relate the two to each other. Related to the point that the additive SNP factor, its interpretation depends on the control variables, the way to think about the PGI that you're getting out of a GWAS is that it's a proxy, it's the standardized noisy measure of the particular additive SNP factor that has the same control variables as the ones that were used in the GWAS. Okay, so I would argue that in economic applications, what we're generally more interested in, even when we use PGIs, is not the effect of the PGI itself, but the effect of the underlying additive SNP factor that it's proxying for. But why is that? Well, because it's partly because the additive SNP factor is based on the true genetic effects, even though we don't know them. And it's kind of arbitrary to look at results that are based on a particular PGI, because those results are going to depend on the particular PGI you happen to have, which depends on things like the GWAS sample size, the construction method that you use for the PGI. And so if we want to get, so in addition to being, I think, both theoretically more desirable, our results will be more comparable across papers if we put them in terms of the units of the additive SNP factor. So when you think about it that way, whenever the PGI is included as a regressor, there's an errors and variables bias, relative to what you would have gotten from the additive snip factor. And it's crucial to do a measurement error correction. So it looks like there's a little bit of a mismatch in the formatting of PowerPoint from my computer to this computer. There's a comment that I could have made about a lot of the papers here. Oh, by the way, I should have said I'm going to use this talk partly as a soapbox for me to preach. So here's the, one. You've already heard some of that. Here's some more preaching. I could have made a comment in a lot of the papers presented that we should do measurement error corrections, but I'm saved us all time. I'm just saying it now. Do measurement error corrections because I think that's ultimately the thing that we're interested in. And there's several methods for doing that. Okay, so coming back to our interest in causal effects, the way we've tried to deal with the issue of causal effects until very recently has been that in the GWAS we control for principal components. That's kind of the best we could do. And then we test whether the results we're getting are the result of biases from not having, from, for example, population stratification or other kinds of gene-environment correlation. We've done that by testing robustness of our GWAS results in sibling samples using family fixed effects. So we've done that going back to EA1 and in all of the EA GWAS and many other papers. So one thing you can do with this kind of approach is ask how much of the results that you're getting from the GWAS are plausibly due to causal effects. So let me show you some an example of this kind of analysis from EA4, which should be coming out soon. So this is based on the EA4 PGI, which is based on a GWAS of about 3 million people, and the R squared of the PGI is about 15% in European ancestry populations. So what this is showing is using the EA PGI to predict a number of different phenotypes. In orange is showing the effect size in standardized units on that phenotype. And then in green is the effect size when you put in family fixed effects. So this is from 3 sibling samples, meta-analyzed from the UK Biobank, the Swedish Twin Registry, and Generation Scotland. So let me just mention a couple of these results. So EA itself is here. So this is using the EA PGI to predict EA. And you can see that the predictive power is cut in half. The coefficient is about half the size when you look within family. For predicting income, it's also cut in half. For using the EA PGI to predict BMI, there seems to be a bit less attenuation, but in general, it's roughly about half on average across these phenotypes. Yeah.
Can you define what you mean by causal effect? Do you mean an average treatment effect across what population, what environments are we talking about?
Yeah. So what I mean is, so what? It's a little bit trickier in the context of a PGI, and I'll say more about this later. But roughly speaking, what it means is if we imagine the hypothetical experiment of randomly assigning someone a different PGI at birth, what would be the effect on their ultimate phenotype?
Okay, so I would think of this as an average treatment effect for whatever population.
For whatever population we're studying, yes. Okay. Yeah, so in this, yeah. Okay, so that's one way to use sibling data is to look at robustness of GWAS results. What about just doing a GWAS using sibling data to actually get at these causal estimates? So that hasn't been possible until recently because the sibling samples just haven't been large enough. And that's why we've done this strategy of doing the GWAS and then looking at robustness. But now they're starting to be large enough samples to make that feasible. So there's a paper that SSGAC is a part of. It's led by some folks at Bristol, Lawrence Howe, and doing this SIB difference GWAS with family fixed effects it studied combined 19 different data sets to get 180,000 siblings in total, and looked at 25 different phenotypes. So here's the kind of result you can get from it.
Just
yeah.
question. Is this, how do we know that there's siblings in this data? Or is it like determined by the genetic data? Or
So generally these are data sets that that are either twin studies that we're focusing on the dizygotic twins, or they're family-based sampling frames where they're using the siblings within a family. It's typical in quality control to, when you actually analyze genetic data, to confirm that these are in fact biological siblings, and you throw out the cases where they're not. So here's, so you can ignore the difference between these two different colors. It basically has to do with this is based on a subset of the SNPs that are either genome-wise significant or significant at some more liberal threshold. And what it's showing for a set of different phenotypes, which are the rows here, is the ratio or the percentage shrinkage from the population effects that you would get from using the between family variation, the typical kind of GWAS variation, to focusing on the SIB difference effects. So just, again, to give a couple examples, for education, it's about 40%, which is to say that the estimates at the SNP level, the effect sizes are about 40% smaller on average when you look between siblings than you get in the population. If you look for height, it's a smaller amount of shrinkage, just about 10 or 15%, and they're seeing no shrinkage for BMI. Here's another kind of thing you can do in this GWAS. This is looking at SNP heritability estimates. These are from LD score regression. Here the blue is from the population estimates, and the yellow is from the within sibling estimates. So again, looking at education as an example, it's about 15% or 17% in the population estimates, and down to 4% in the within between siblings. So that big difference is actually, probably a lot of that is due to assortative mating on education, which makes the population variance explained much larger. Yeah.
Isn't this 4% surprisingly small? Even with like PGS, you can get higher heritabilities between siblings.
Yeah, so I mean, there's problems with all of these ways of estimating SNP heritability. So I think these are probably biased downward. I think what's more interesting than the magnitudes are the differences between the population and within SIB.
But just on the point, I just worry that people say this and just start commenting, oh, like there's nothing about, like there's no effect of genetics on education. There's only 4%. Even like that, I worry. Just people misinterpreting the number.
I mean, I think we just shouldn't be using LD score regression for doing this. We should be using, RDR, or something that has a lot less bias for the estimates.
And RDR is much higher, right? I think Alex's paper is like 10 or something.
I don't remember off the top of my head, but yeah, it's higher than this. Again, for height, there's less of a difference here. And you can do this for a lot of different phenotypes. This is another interesting thing you can do with this kind of GWAS result, which is look at the genetic correlations and contrast the genetic correlations that come from the population effects, which again are in green, versus those that come from the within sibling results. So, for example, BMI has a moderate negative genetic correlation with educational attainment in the population results, but when you look within SIBs, that appears to be much smaller. It's not statistically distinguishable from zero. However, the standard error, the confidence intervals are pretty wide, so I'm not sure we can conclude that much yet about these genetic correlations from this particular within SIB GWAS, but it points at the kinds of conclusions we'll be able to draw as we can do this in larger samples. Okay, so in the sibling, so this is it is a pretty powerful approach. In the sibling data, the family fixed effects eliminate all confounding from gene environment correlation that is between family. So that includes population stratification and parental indirect effects that have come up, and I'll talk more about that later. And this is again something that I don't think we certainly didn't appreciate it until a few years ago. It does not eliminate confounding from sibling indirect effects. So I'll make that point more precise now. So what I want to do next is explain what do we mean by these terms: direct effects, sibling indirect effects, and why. How can you see that there's this bias from doing the SIB difference GWAS? Okay, so we have so now I'm going to use J to denote the different siblings in some family I, and I'm going to use this general approach to deriving an additive model, but now that we already talked about. But now I'm going to specifically make the set of control variables the sibling genotypes, which I'm going to call xi j prime, and the parental genotypes that I'm going to write this way: the father of I and the mother of I. So we run that population regression. We get some coefficient on one's own genotype vector, and I'm going to call that coefficient beta self. We get the coefficient on the sibling genotype. I'm going to call that beta sib. We get the paternal and maternal coefficients, and then some error term. Again, by construction of the population regression, this error term is going to be orthogonal to all of the regressors. And what's different now, it's special in this context, is that because of meiosis, both xij and xij prime are random, conditional on the parental genotypes. So both of these two terms, both of these two betas, beta self and beta sib, have a causal interpretation. They're both average causal effects. And this beta self is what I'm going to call the direct effect, and the direct effects of the SNPs, and beta sib is the sibling indirect effect. Yeah?
Maybe you're going to think this is too much detail, but and this is a number of the papers do this. Throwing these variables into the regression, it's not conditioning on them exactly, right? You're not allowing for a fully kind of condition on them in sort of a non-parametric way, because everything always seems to be linear and additive in everything everyone's doing. I'm just wondering if that's something that people have ever thought about. Well, why is there always these kinds of functions? And should I be satisfied with this? Because I think the primitive condition is just a condition on each level of the parents.
Yeah. So you could do this. Yeah, it's a good point. It's actually something I've thought about writing out more explicitly, and maybe we should do that to just be even more, more fundamental. But you can do this by conditioning on the grandparental genotype, so the father's genotype, the father's mother's genotype. So you get just 0, 1 variables, binary variables for all of these x's, and it all works out. And that's completely, that doesn't build in any linearity assumption at all.
And you get the same result that everyone else does?
You get the same result. Yeah.
Okay. Well, that's reassuring.
Yeah.
Thank you for doing this, by the way. I don't mean to. I'm asking you.
No. It's a good question, and you've pushed me. I've been not sure whether we should do that or not, but your question has been helpful. Pushed me in it. Now I'm thinking more. We probably should do that. Yeah.
I will never be a referee. So.
Yeah. No, but just I think it's useful to really understand deeply what's going on here. Yeah.
Yeah. Following on Matt's question, I think this is a useful set of regressions. What I'm very uneasy with is the use of the word causal, and the reason for that awkwardness on my part. Where does the Z comes from, and what's in it? And what I have in mind is that there are some other factors that affect the phenotype, the manifestation of educational attainment, which depend on parental behavior, which is not fixed. I mean, it can be affected by the XBI, but it's not fixed. Depends on public policy, depends on the school availability, it depends on a variety of factors. And those factors can be correlated with the genotypes, with the individual genotypes, so the simply put genotypes. So what does it mean to call that beta a causal effect?
Yeah, so I think, I mean, tell me if I'm not following the question, but I think what you're pointing out is that there could be environmental factors or, that are affected. Someone with a particular genotype, may select into certain environments, say, and in those environments may be affected by those environments in ways that ultimately affect their educational attainment. And it was the environment that mattered, not ultimately the genotype.
And the fact that the X's are random conditional, I buy that. The X's are random conditional parental genotypes does not mean that they are uncorrelated with the Z, with the error.
Well, they're uncorrelated with this error by we run the population regression and we get that all of these X's are uncorrelated with the error, and then because we condition on the parental genotypes, we get random assignment, full random assignment independence of Xi j and Xij prime from all variables. But you're right that the mechanism, so these are average treatment effects in a fully reduced form sense. The sense being that if at conception we randomly manipulate your genotype, there will be, we're predicting what the outcome is going to ultimately be on your educational attainment. And it could be through mechanisms that we would call environmental mechanisms. It could be because with a certain genotype, you select into a different kind of environment that then ends up affecting your educational attainment. All of that, in this framework, all of that is being assigned as a causal effect of genotype, even though we would naturally call it environmental. And that actually relates to another common misunderstanding, which is people think naturally that what these models are doing is decomposing genes and environment, and that's not what they're doing. Anything which is affected by genotype, including environmental mechanisms, are being assigned to genotype, and the residual is just capturing anything which is not one of those factors that matters.
Yeah, but that, suppose that you could.
Horacio, can you speak up a little bit?
I'm sorry.
Yeah, thank you.
Suppose that you could manipulate the genes. Suppose you can really change the Xij. What I'm claiming is that the beta self is not going to give you that, because by that manipulation it would also trigger a chain of other effects and factors that are not captured there, that they are in the Z. I know that you run the regression by construction, by the OLS. The estimated Z is going to be orthogonal to the rest of it. But the parameter you're estimating is not the structural parameter. It doesn't describe the causal link from X to Y. That's the point I'm making.
I agree it's not a causal parameter, but could you give an example of the kind of...
Suppose that a certain genotype is reflected on a certain type of behavior by the child, and that type of behavior triggers a reaction from the parents in terms of parenting style, say.
Yeah, that's part of beta.
This is about an interpretation, right? So we wrote a review about this, and basically you have to evocative and what's active gene environment. I suppose. The causal effect is not purely biological. You can have environments that you select into, or you can have environments that respond to you, and all of that is part of it, right?
Yeah, that's right. So this, it's a very important point. This is not a structural model, and I think that one way in which economists can contribute to this literature is thinking more carefully, writing down more structural models, and thinking about mechanisms. But the framework that geneticists and behavior geneticists have been using is this one, which is fully reduced form, and where the things that are getting attributed to heritability in twin studies are including the kinds of mechanisms that you're talking about and calling them part of the genetic effect.
It's just the issue of calling it the average causal effect as opposed to the pseudo-true value. Think about what you're really doing there is that you're getting the pseudo-true value of the population mean, right? Which is everything that is in that correlation, what would converge to. That includes, if we're thinking of an econometrician, we would have think about C as psi as just some random effect. But that's going to be correlated with the x's, and when you do those things, the correlation we just talked about. What you get beta is the true value, right, which include the actual direct effects to every type of mechanism and behavioral and stuff. And going back to David Hendry's work and stuff like that, that's what we would call the true value, as opposed to the average causal effect.
What's the term you're using?
Pseudo-true value.
Pseudo-true value? Okay, I'm not familiar with that terminology, but
So
I mean,
that's what it converged to. And so you can have bias, what we would call biases of the econometrician, but what you're saying is included. In
yeah.
data.
I mean, I think that the terminology. Maybe we should talk about this offline. But I think this terminology is consistent with the way that the term average treatment effect is used in the randomized, the kind of Rubin causal model, randomized evaluation framework, where that's also the case that you do some intervention, and it can have effects through whatever mechanism, and they're all getting us. It's all being considered part of the average treatment effect.
I don't buy that because implicitly you're saying, okay, I accept that. In my example earlier, when you have a shift in parental behavior, that's reflected in the beta. But implicitly, what you're saying is if you can manipulate the axis, the beta will change as well. And therefore, the beta does not reflect the beta that you have, which comes from a given set of parental behavior, will not reflect the effect of a change in X on Y.
I think that in a large population, if you just change a single person's X, and the betas are defined as the average effects across people, it's not going to change. But maybe we should talk later. Okay. Okay. So family fixed effects. So what I want to do now is think about my claim before that when you think about the SIB difference approach, you have a confound with the sibling indirect effects. So let me just make that argument formally. When you include family fixed effects, that's equivalent to estimating the SIB difference model. So that's this model here. And you can if you just take this equation and write it also for yij prime and subtract, what you get is this equation where you have this uncorrelatedness. So this regression is going to identify the difference between beta self and beta SIB. So that shows the direct effects are in this context perfectly confounded with the sibling indirect effects. Okay, so now what I want to do is think about how could we get at what do we mean by direct effect PGIs, and what happens if instead of doing sibling differences, we control for parental genotypes. Okay, so now going back to the additive model, but now the set of controls I'm going to include are just the parental genotype vectors. So now we get this population regression. So again, the one's own genotype is random, conditional on the parental genotypes. So the direct effects have a causal interpretation. They're, again, this weighted average, again, reduced form, all the same caveats we were just talking about apply to the interpretation. And they're this average treatment effect from modifying the genotype at conception. So now I want to ask a question of how does this, I just called this the direct effect, but I also called this beta self from the sibling model a direct effect. How do they relate to each other? are there two different kinds of concepts of direct effect that we're talking about depending on whether we're doing a SIB difference or a parental controls? So the answer is they're equal to each other. So they're not two different concepts. They're the same thing. Here's the argument. Since your own genotype is random, conditional on your parents, there's no omitted variable bias from having omitted the sibling. So even if there really are sibling indirect effects, you can omit them and still get an unbiased estimate on the own genotype. So the two betas are equal to each other. There's a nuance here, which is that when you do sibling studies, you're focusing on the population of families with at least 2 children. When you control for parental genotypes, you don't have to make that sample restriction. You can also study families with just 1 child. And there could potentially be a difference in betas in those 2 populations. But apart from that, they're the same concept. What about parental indirect effects? So I haven't mentioned those. And the reason I haven't mentioned them is that they are not identified. So when we run regressions that include the parental genotypes, we have the random assignment of the child's genotype conditional on the parents, but we don't have random assignment of the parents' genotypes. So the coefficients on the parents' genotypes are picking up all of the bias that otherwise would have lived elsewhere. So it's picking up population stratification biases, assortative mating biases, so gene-environment correlation. The sibling indirects are showing up in the coefficients on the parents. So I'll make the bold claim, I'm pretty sure it's true, that although parental indirect effects have been an enticing and certainly a plausible idea, we have no evidence for them in humans. I mean, at least for the kinds of phenotypes we've been talking about. So, the nature of nurture paper and all of that, all of that evidence is confounded. So back on my soapbox, don't refer to these coefficients on the parental PGIs as parental indirect effects, because that's not necessarily what they are. Let's call them something more neutral, like parental coefficients or something, and acknowledge that they have these other biases. So we really don't know what the magnitudes are of these parental indirect effects.
Sorry.
Yeah.
That means that you're saying that the indirect effect is like the parental environment that relates to their genes. Okay, you're saying that why do you say this, that this is not the case?
So I'm saying, by parental indirect effects, what people have in mind is actually the population regression, where you're regressing on individuals' genotypes, their parents' genotypes, and the parents' genotypes, the grandparental genotypes. Then you have random assignment of the parents' genotypes. And then a coefficient on the parents' genotypes is telling you that somehow the parents' phenotype, their behavior that is creating some environment for the child that's mattering for the child's outcome, that's not working through the child's own genotype. But without the controls for the parental genotypes, we don't have random assignment of the parental genotypes. So there's other things that could lead to a non-zero coefficient on the parental genotypes, like family socioeconomic status, which is going to be correlated with the parental genotypes. So that's a kind of gene-environment correlation. Okay, so now to say what the direct effects are, I'm just going to take this equation where we've controlled for the parental genotypes, and I'm just going to do a change of variables where I'm going to substitute in this additive Snip factor G for the X beta, and then delta is this standard deviation that we need to make this come out to X beta. So this delta is what we mean by the direct effect of the PGI, or the direct effect of the additive Snip factor, which is the thing that we're going to be estimating with the PGI. So that there's a subtle distinction I'm drawing here between the beta here is the vector of direct effects of the SNPs. But now I'm going to move to talking about the direct effect of the PGI. And to do that, I need to define what I mean by that direct effect of the PGI, and that's this delta, which is coming from the direct effect of the SNPs. But now, this thing is what the coefficient on the PGI is going to correspond to. So this comes back to that question of interpretation from earlier about the experiment, that it's more complicated. The sense in which this thing is going to be causal is more complicated than in the sense of an individual SNP. For an individual SNP, we can talk about the hypothetical experiment of changing the genotype at conception. But for a PGI, you could change lots of different SNPs and have the same effect on the PGI. So that's okay. I mean, because on average, we're saying that, we're talking about the average effect, but so the hypothetical experiment you have to have in mind is kind of like changing each of these things and then kind of taking an average over the whole thing. So that's the sort of causal experiment we have in mind. And then there's an additional complication that if we haven't measured all the genetic variants in the genome, some of what's getting picked up by the PGI is unmeasured causal variance. And so that part of it is not really causal. It's just proxying for causal variation elsewhere in the genome, but it's still giving us a measure of causal effects that are happening somewhere in the genome. Yeah, Kevin.
Maybe this is absolutely equivalent to how you characterize thinking about an average, like a one-unit change in the score. I mean, one way to think about it is, say, starting from whatever PGI you got at conception, imagine randomly drawing from the distribution of SNPs that would generate a value of the polygenic score that is one standard, 1 unit higher, or something.
Yeah, that's exactly what I mean.
Yeah,
Yeah. That's exactly right. Yeah. Okay, so now I want to come back to sibling data and ask, if the thing we want to do is, really control for the parental values, the parental genotypes, and not do the SIB difference model because we want to eliminate the bias, is there something we can do with the sibling data? And the answer is yes, we can use this imputation that's come up a few times at the conference. So let me just talk about that for a few minutes. So there's a benefit to controlling for the parental genotypes rather than using the sibling fixed effects, and that is that you don't have this confounding from the sibling indirect effect. But we often don't observe the parental genotypes. But there's there's a method. There's actually more than one, but I think the best method is the one by Alex Young and Augie Kong and colleagues that imputes the parental genotypes from other family data, including siblings. So often when we talk about imputation, we're using linear imputation methods that don't add any information if you're ultimately going to run a regression. What's special in this context is that Mendelian inheritance is a nonlinear process. And so by using that process to do the imputation, we're essentially adding information that we didn't have in just the sibling data. So I think that's an important intuition for why you can actually get more precise results after you do the imputation than you would have gotten from just sibling data. And I'm going to show you that in a moment. So that means there's actually two advantages to doing this parental imputation when you have sibling data. First, it reduces bias because it eliminates this bias from the sibling indirect effects. And also, it increases power because it's adding some information. So, soapbox again, do this. A lot of the papers did, which is great. If you have sibling data, I recommend doing this parental imputation and then controlling for parental genotypes. So here's the power gain. I don't want to spend much time on this. There's different ways of doing the imputation, but the black line may be the best one to focus on. That's involves some more processing of the genetic data before you can implement it, but it's all been automated by the software that Alex has written. The power gains depend on the correlation between the siblings' residuals. So the best case scenario is that they're uncorrelated, And in that case, relative to using the SIB differences, the sample size gain is equivalent to having a sample size that's a third larger in terms of the standard errors that you would get. Yeah.
So these gains exist even if you moved away from your linear model and moved to something very general, so you have a nonlinear model relating y and all of these variables.
So
Do I need some difference? Do I need a parametric restriction on your y in order to gain any power or identify it at all using this imputation?
yeah, we're not sure. We conjecture that the answer is it would still work and give you consistent estimates and give you gains in power with nonlinear functions, but we don't know that for sure and hasn't been proven.
Okay.
So there's also gains in power for the parental coefficients, and these gains could be up to 50% in terms of sample size. Okay. So
Dave, you have about 5 minutes.
yeah, good. Okay, so I'll mention that we're now pursuing this idea. So better than the SIB difference GWAS would be doing a direct effect GWAS where you're controlling for the parental genotypes. We're pursuing that now. This is a project that Alex Young is leading with the SSGAC. So the effective sample size is gonna end up being it's already with the partial data. It's the amount of power is equivalent to having twice as big a sample size as the Howe et al. Paper, but it's going to be effectively as well sampled as EA1 with about 100,000 people once all the data are in. We're looking at a bunch of phenotypes. So I'll just highlight one interim result is we can get estimates of the correlation between the direct and population effects. So this is for EA. We're estimating about 0.7 as of now. Okay, so let me end with a few thoughts on applications using PGIs, trying to isolate within family variation. So the first question I want to ask is, how can you, if you want to study a PGI, so we've just been talking about genotypes pretty much within family, but let's say we want to study a PGI within family, how would you control for the parental genetic variation? The usual approach is to control for the parental PGIs, constructed using the same weights that you use to construct an individual's own PGI. But to me, it's not obvious that that is the right thing to do, right? That that's going to get you the thing that you really want. Now, I wanted a twist in my talk. So my twist is I've been telling you all these things that are wrong, that people thought that were wrong. This is actually something people were doing, but it's actually right. But let me first show you why, how you might have thought about it based on the kind of way we've been thinking about other things. So let's say we want to estimate, the problem is we want to estimate the causal effect of some weighted sum of genotypes. So I'm going to call that a PGI. And I'm going to allow this to be an arbitrary weight vector. So this could be a within family PGI, could be a population PGI based on a regular GWAS, could be a principal component, could be a single genetic variant where we put all the weight on one variant. So the thing you think about based on the way I've done this talk so far is that because this PGI is random conditional on the parental genotypes, you would run this regression conditioned on the parental genotypes, and then you have random assignment of the PGI. Problem is, you can't actually run this regression because we would fail the rank condition if we included the full genotype vectors of the parents. And we can't construct these variables because these are different weight vectors, these betas, and we don't know them. So here's why it works to regress on the parental PGIs. And actually, the thing that really, what's sufficient is to regress on the mean of the parental PGIs. And the argument is that you can decompose this PGI, this whatever the weight vector is, into two orthogonal components. One which is the between family component, which is the average PGI of the parents, and one which is the within family component, which is the difference between the actual PGI and that parental mean. And those components you can show are orthogonal to each other. And so, after you've done that, so once you include this control, you then have essentially, random variation in this PGI. And then this is sufficient, but you can get even more power by instead of fixing the coefficients to be equal on the two parental PGIs, allowing them to vary, which is effectively what people are doing in practice. Okay, so this is the last slide, just to summarize, the kind of suggestions that I'm making. First, when working with family data, impute the parental genotypes. And we're going to try to make that easier in the next version of the PGI repository. In the family data sets, we're going to impute parental PGIs, parental genotypes, and construct parental PGIs so that users can just download them. When you're analyzing the PGI, identify the causal effects by controlling for the parental PGIs. Don't refer to the coefficients that you get on the parental PGIs as the parental indirect effect. Disattenuate the coefficient on the PGI. There's a slight subtlety with the use of some current methods for doing the measurement error correction because they didn't allow for the controlling for the parental PGIs, but that's recently been generalized to now have the adjustment that controls for the parental PGIs. And then finally, the common practice today, because we don't yet have these large within family GWAS, is to use the GWAS, the PGIs from population GWAS, and then look at within family variation. If you want to interpret, that's different than the direct effect of the PGI that you would get from the within family GWAS. And there's some papers that work through what that bias is. So that's something else that should be acknowledged the way the work is being done now. Great.
I know you have to leave. You want?
Yeah, I could take it. I think it's time for a couple questions. Yeah.
So I wanted to come back to the language that we're using when we talk about direct causal effects. And I actually think that the way that we've been using the terminology in the community is contributing a lot to misunderstandings and pushback that we're getting from non-geneticists. And maybe a good example for that is the famous red hair example, where you think of a system where there's systematic discrimination against people with red hair, and they may not be allowed to go to school. And then if you run a GWAS on high school, college attendance, or whatever, you've got that gene that causes you to have red hair. Then even in this framework, where you may have randomly assigned genotypes between siblings, it is actually very misleading to call that a direct effect of the gene, because it is ultimately caused by the environment that induced the genetic correlation in the first place.
Yeah, I totally agree. I think this direct indirect language is very bad, and I'm the only reason I haven't yet proposed the shift in terminology is that I haven't been able to decide what's a better term to use. But I'm open for suggestions, and I think we as a community, once we find better terms that are more descriptive of what we mean by direct and indirect, we should switch terminology. Yeah.
I think there's two issues. One is kind of probably the first order issue, which is all the interpretation issues that Orazio brought up. And I think everyone agrees there's some issue there, and you need some model maybe to think about. It's maybe not just a shift in language, but it's really, it's not just a disclaimer that people put this is not a causal effect for this, or this is not primitive. But I think the other issue is, when I see this estimation now, it's strange to me, all these regressions, in the sense that there's this entire literature in economics about matching, which is non-parametric OLS. And there, the language is very clear. We're matching on certain variables. In this case, you're matching on the parental genotypes. And they would never claim that there's a causal relation. The difference in going from one cell that you match onto another cell is not some causal thing, right? And so they're very comfortable with not calling that anything. You're just matching on certain variables to satisfy a conditional independence assumption. And I feel like I don't know why this literature doesn't think about it exactly that way, because then all the issues about what I think is interesting here is the overlap. The overlap in the support of the variation in the kid's genes, conditional on the parents' genes. And it might actually be different. I don't even know. Maybe you guys know. Probably do. Are certain parent genotypes have more variation or different kinds of variation in the kid's genes? All of it's random, but different kinds of variation that's random. So, for example, it's moving more for certain kinds of families than other kinds of families. And that matters for the weighting that you're getting out of your regression, because you're overweighting where there's more variation, for example. So it's not really an equally weighted average. But all of these issues, I think, are somewhere buried in kind of the matching literature and the treatment effects literature. And I'm surprised, I guess, that it's not more here. So that's just it's more of a comment. You don't have to say, hey.
Yeah. So
I'm curious what the history of this, and it might be because of.
Yeah, I mean, I think the history is that the literature hasn't been careful at all about thinking about what are the what's fundamentally being assumed. Where is this additive model coming from? And so I mean, I think I think we made a lot of progress in terms of relating what we're doing to things we understand, like regressions and treatment effects. But I take your point that there's probably more progress that could be made by incorporating more of what we've learned in the econometrics literature to further develop the way we're thinking about these problems. Because this is, I mean, these models go back a century, but geneticists just haven't thought about it in this way. They generally just write down an additive model and just say assume an additive model and don't say where it's coming from.
Yeah, it's not necessarily the additivity per se. I mean, there's a whole set of estimation techniques, a whole set of econometrics that deal exactly with this issue. You have a conditional independence assumption, and you need to now implement it in practice and estimate it. They think very seriously about this. As a whole, people win Nobel Prizes for this. So, I think there's obviously a lot of room. That's not what I do, but I think there's a lot of room for some collaboration on that element of this. And again, I think that's a second order issue. That's the estimation issue. I think the first order issue is Orazio's issue, but I wanted to bring that up.
Yep.
Sorry to intervene again. To follow up on what Matt says, I think this is incredibly useful. And, I've learned a lot over these 2 days from this conference. If I put my economist hat on, and if I think that way, I think what we as economists can contribute to this literature is to incorporate in all this behavior. And so we need to write models of behavior and how people react to incentives that react to these observations of phenotypes and so channel the effect that genetic influences might have on the environment through models of behavior. They will be perfect. There will be the inference will be conditional on the type of models we use. But I generally think that this is the contribution that as economists we can make. And the first step is to clarify what is causal, what is direct and indirect. I completely agree with that. But then from there, we need to add dynamics is important, behavior is important.
I totally agree, and I think we've seen a couple examples in the conference of the dynamic structural, the consumption savings model, and then there was the paper Victor presented on the parental investment. This paper here that I'm citing is actually a structural model along the lines of what you've been suggesting, Orazio, about parents either compensating or reacting to differences between siblings. I think that I totally agree that economists can contribute to this literature by bringing that kind of methodology in.
So we'll have to unfortunately wrap it up there and take our 5-minute break and then go into our next session of Frontiers. So let's give Dan another thank you.